Hello everyone and welcome to this new video about level design. In this episode, we're gonna talk about a fundamental concept for procedural level generation, terrain data encoding. Before we dive in, a big thank to Cellular who suggested the topic for this episode. If you too have some ideas for other level design videos, don't hesitate to drop a comment down below or on my Twitter. And with that said, let's get back to our procedural generation. Now, if I were to ask you to describe a super basic level like this one, you could probably analyze it with different levels of abstraction. You could be all about game mechanics and talk about an entry point, a danger zone, and an exit. You could take a bird's eye view of this level as part of a larger game and regard it as a tutorial or an introductory level for the spike or the basic player movement. Or you could even be very factual and say that it is a set of tiles with a grass tile, then another grass tile, then a slope, then an empty space, then spikes, etc. This third type of description might look boring to us humans, because we are trained to see patterns everywhere and we instantly recognize all of this. So our brains don't actually need a listing to get the gist. But if you need to implement a level like this one, there's a moment where you will need to specify that you want these specific tiles to be placed at these specific coordinates. Otherwise, the machine won't be able to show anything to the players. The problem, however, is that even something as obvious to us as put a grass tile in the bottom left corner is complete gibberish for a computer, because computers only understand numbers. They don't have the notion of a wall, a spike, or a door like we do. So whenever you work hand in hand with the machine, and typically for level creation, be it procedural or not, the first step is usually to encode your concepts in some way so that they can be fed as numbers to the algorithm. For example, consider a common case for procedural level generation, the creation of a dungeon map for a little roguelike. A frequent technique here is to create a mapping table between an arbitrary unique index and a tile type. Once this is defined, then the computer can actually translate between those two representations and help you create the level. Now the question is, how do we actually automate the generation of something like a dungeon map? The simplest approach would be to just take our entire grid of tiles and pick a tile type at random in a list for each slot. This naive algorithm would give results like this dungeon, for example. Of course, this is clearly not the right way to go. This level doesn't make any sense and it's not valid because we don't have a path for a hero to the exit. As we said in the first episode about procedural generation, this design philosophy is not about using pure randomness, but rather controlled randomness. In this case, it would mean picking tiles at random in a subset that is valid for this given spot, or exploring some graph theory algorithms to ensure we always have a correct flow in our level. There are many tools to do this job, but one that is quite famous in the game dev community is the Cellular automaton. In short, the idea behind Cellular automata is to discretize your given chunk of space into a grid of cells, and then give each cell a finite number of states. For example, in the simplest case, active or inactive. Then you're going to transform this grid of cells gradually by iterating a generation counter and morphing this initial state into something else. To know how the board should transform at each generation, you'll rely on rules. These rules will decide how the state of a cell should evolve, considering the state of its 8 neighbor cells. For example, we could have a rule that says that if less than 2 neighbors are active, then this cell will turn off next turn. Conversely, if there are exactly 3 neighbor active cells, then this cell will turn on next time, or stay on if it's already active. This may seem too restrictive at a first glance, but these kind of simplistic rules actually make for amazing systems. Thanks to a principle called emergence, each single rule combines with the others and the current state of the grid to create truly incredible effects, such as Conway's well-known Game of Life, which is one of the most famous examples of a cellular automaton. For procedural level generation, cellular automata can be a great way to create caves or dungeons. And by adding more states than just the active and inactive we have here, we can even make multi-area maps like those ones. By the way, if you're curious, the Python code that generated those views is available for free in the description of this video. And there's also the link to the blog post that describes the whole process behind this. To sum up, you have to remember that computers are strange beasts that can perform computations blazingly fast, but are also quite dumb when it comes to perceiving reality. In order to work, they have to be fed the right data and the right algorithms, which means you'll have to abstract and encode your problem the right way. But once you're done and you've told the machine what to do, you are in for one hell of a ride. Anyway, that's it for today. I hope you enjoyed this quick episode about level design and procedural generation, and that you learned a few things about how to converse with a computer in numbers. If you did, feel free to like the video and subscribe to the channel. And of course, don't hesitate to leave a comment with your own ideas for future level design tutorials. As always, thanks a lot for watching, and take care.